Okay, so we're ready. So I'll start with the introduction. Thank you, Kaan, for coming today. So today we have Kaan, who is an associate professor in the computer science department at University College London, where he leads the computational light laboratory. So his work is at the intersection of light and computation, including computational approaches in imaging, graphics, fabrication, and displays. So he's widely known among the optics and graphics community for his many contributions to display technologies dedicated to virtual reality, augmented reality, and three-dimensional displays with glasses and without glasses. So he was previously a research scientist at NVIDIA in the US between 2014 and 2020. And his work has received many awards, including Emerging Technologies Best in Show at SIGGRAPH, several of them, and Best Papers at ISMAR and IEEE. So I hope that was fine. And now, Kaan, you can go ahead with your talk.
Yeah. Thank you, Anna, for your kind invitation, and thank you for the nice introduction too. Thank you, everyone, for having me here today. As Anna just introduced me, my name is Kaan Akşit, and I'll be talking about perceptually guided computer-generated holography in this talk. So before preparing my talk, I took a look at the map and tried to see like how far am I from you guys. And according to Google Maps, if I decide to walk from where I am currently to where you are in Spain, roughly it's like 243 hours. It's a very long journey. And suppose if you want to visit me by doing the reverse, perhaps with a more reasonable approach, as you arrive in London, one of the main train stations, Euston train station in London, you will immediately find our building. It's right across the street. It's a beautiful building located in the center of London. In this building, you'll find lots of offices and various different laboratories. So both my office and my laboratory they are located in the very same building. And here you see a photograph taken some time ago showing benches from my laboratory. We are equipped to conduct research in various different branches, including optics, graphics, and visual perception. Next, I would like to give you some idea about where I come from, what I do, what's my intention, what's my lab's motivation, and so on. So here I show a timeline. I joined University College London back in 2021, a year ago, in the computer science department and as an associate professor. I started my own research group, Computational Light Laboratory. Previously, I was a senior research scientist at NVIDIA in the United States, where I helped co-found a research group dedicated to virtual and augmented reality applications. After spending years in the industry, I moved back to academia with one goal in mind: to help shape young minds and get their attention to tackling a critical problem, the future of displays. In a second, I will talk about why displays are so important, why should we care about displays in the first place, and why its research is highly important for our societies. But before coming to that, I would like to highlight I've been in other places in the past before. These institutions include Koç University in Turkey, Disney Research in Switzerland, Philips Research in Netherlands, and RWTH Aachen University in Germany. So people know me primarily for my contributions in augmented reality displays, near-eye displays, and 3D displays. And many of these works, as Anna told, already received multiple awards. So next, I want to bring you a slide discussing more about our most noticeable research from the recent years. A quick summary goes as follows. On the left-hand side, you see a film being placed in front of a mobile phone and converting that mobile phone into a near-eye light field display. We made such a prototype back in 2015, and we showed that you can convert a display this way into a mobile phone just using a very thin sheet of film In 2017, much before the leading industries, we looked into more advanced version of that light field approach by taking into account perception. We looked into the idea of varifocal displays. Assume you know where the person is looking at in a given scene. You can change the focus of the display to a specific place, specific location on the scene, so that you present the right focus cues in a display. This is computational less expensive. That's why it's interesting, because it simplifies your hardware quite a lot. Although in these implementations they have bulky form factors, it could also be shrink down. There are evidence for these things, which you can find from coming out of industry research labs in the recent years. And in 2019, we looked into the trend of 3D fabrication, 3D printers, and so on. We ask ourselves, like, can we make this so easy that you can just 3D print your display using your own 3D printer? This was the basic idea, because as you know, the 3D printers promises this approach of updating everything on the fly. All you need to have is the raw material and the 3D printer, and that's what we followed. Basically, we showed that most of the components in a near-eye display could be 3D printed. This way you can make a very cheap and highly effective near-eye display using 3D printers that supports your application. Back in 2018, 2020 timeframe, we looked into foveated displays. The foveated displays could be explained like, if I know where you're looking at, I need to provide the high resolution image at locations where you're looking at. However, in your peripheral vision, in large eccentricities, you don't perceive most of the details of the content. Therefore, can I use a lesser amount of pixels in your peripheral? This is the basic idea behind foveated displays, and we actually built something similar to this description. We built a picture-in-picture display in which there is a high-resolution image at some location representing your gaze location, and then there's this low-resolution image, but it's expanding to a wider field of view. So we also introduced many different other methods for displays. I think two noticeable ones are the one related to prescription, shown on the top right-hand side. This is a display that accounts for your prescription and changes its characteristics accordingly, both for your virtual content and your real-life scene. So it's a prescription glass built-in display, I would say. And at the bottom, you can see this another display type which we built. It's an unconventional display. Rather than using pixels, we ask ourselves, can we use image patches, just like JPEG, right? JPEG compression. Can I stamp image patches rather than pixels? That is the general idea behind that display. We have some proof of concept results coming out of that line, and it was interesting, and it helps increasing spatial and temporal resolution of displays. Through scanning and using low resolution spatial light modulators, you can generate high resolution and fast refresh rate displays using this technique. So today I want to focus on the future of display technology. This is the main motivation of my lab and a primary focus in my research group. The reason for that is quite obvious, but I just want to reiterate. So we as a society, as human beings, we spend a tremendous amount of time in front of displays. So in some places, this can be as large as half of our lifetimes. Even right now, we are looking at these two-dimensional displays in this remote setting. I feel like this is kind of pretty weird, in my opinion. It's ineffective. Displays has to offer more, right? Basically, we are locked on our tables looking at two-dimensional displays, and we are trying to survive and communicate and so on using these kind of modalities. I feel like this has to change or transform. It has to be something more human-oriented, in my view, so that we can bring back our previous experiences from real life into these teleconferences. We can have a more effective way of communication, and this will immediately change the way we the business, education, health, everything you can think of. Displays in the future, like they did in the past, they will change our lives. A good example to that is smartphone displays, smartphones that we have. They transformed our lives. Like, just if you try to just imagine, remember the time before your smartphone, it was a different era. So the same thing is likely to happen with the introduction of augmented reality. And there are barriers to get there. We will also talk about that. But my fortune telling here, let's say, or let's call it an educated guess, I think this remote interaction we are having, it will increase in the future, and we have to pay attention. We have to improve our tools to support these interactions. So my laboratory is scientific motivation, invent and build the proof of concept futures display system for humans. You may have heard the same aim from some other libraries, but some other groups, but this for humans part is ours, I think. It's because we are human oriented. We want to have a perceptually pleasing visual experience. Indeed, you can ask, like, what are the challenges? What is the current state of the displays? How one would build the future's display system is another big question, right? Perhaps the right starting point to answer all these questions is about the future itself. We should start from the future and walk back to current time to understand what we need. And we first have to paint a picture of the future. Of course, this is subject to discussion. This is my personal view about how future should look like. But I think in many industries, they share also the common goal. In my opinion, the primary goal of industry and academia is to build a display that paint lifelike three-dimensional visuals right in front of our visual field of view. And these displays will be mobile, will be, forgettable, let's say. You won't even feel. It's like your smartwatch. You don't feel it all the time, but it's on your arm. Like, you can forget about it. It will be similar to that in terms of experience. And these feature displays will help us transform the social interactions that I was pitching earlier, help us to get together again and remove us from this flat teleconferences. And of course, it will provide unseen opportunities in education and entertainment, because now you can introduce three-dimensional visualizations in the proper way, in the natural way, and blend it with the real world. That's also an important aspect of augmented reality. Also, it can transform the businesses and healthcare applications quite a lot in the future. But as you can see from this depiction, the person is standing up, not sitting down, not in front of a table, and not looking at on a two-dimensional flat display. This is the future that I hope to get to, let's say, and it's more human-oriented. I can switch it off whenever I like. I can switch it on, get the necessary information whenever I like, and so on. But at best, in the current day, what we can do is just render three-dimensional visuals on a flat two-dimensional screen. And they're looking realistic. I mean, this is awesome. When you look at the games, they look highly realistic today. But still, they are lacking physical qualities in order to provide a true realism. They are only being shown to us on one depth level, and they are just on a two-dimensional flat screen. So we are not even close to the future I'm describing here. So you can ask yourself, like, are we stuck with this 2D, two-dimensional screens? The answer is maybe or maybe not. We'll see. And again, this is my call. I bet in augmented reality near-eye displays to fix this problem, or to say, to get to the future that we all want from those two-dimensional displays. And I feel like many industries and academia is sharing the same bet, let's say. So industry and academia, they're both pushing forward with near-eye displays, right? And these are for virtual reality and augmented reality applications. These devices are highly complex, contains lots and lots of different components inside it. Cameras, displays, display drivers, optics, computers, coolers, and batteries, on all these things. And the goal is to take these components, each one of them, miniaturize them, and then just pack it into a single variable device. I'll just repeat to let it sink in. So we take cameras, displays, display drivers, optics, computers, and coolers and batteries. We will just miniaturize them, pack it into a single device, and it will become variable. I feel like this is like a moonshot, to be honest with you. There are just too many problems to tackle. Like, there isn't one single human being on this planet that can know about batteries while knowing about display drivers or computers, or like designing a computers and then cameras at the same time. This is something that requires collaboration. This is something that requires people sit together, work on it, and fix it all together. And not many places have the resources to do that. So, some certain big companies betting on this with lots and lots of money. And if they can achieve it, the future will be very different, of course, with this scientific method. If they can achieve it, there will be, a different future for us all. But we should also understand, this is a moonshot, and this involves solving many different problems like heating, form factor, weight, power, compute, convergence, accommodation, complete brightness, and dynamic range. Let's say we can resolve these issues in the future, and we should also talk about the technical details in that respect. What do we want from these displays? We want these displays to be really, really slim, forgettable, so we can just wear it all day, 7/24, and we can use it for our own benefits. And it should be like uninterrupted in terms of power. It shouldn't last just 2 hours. It should last for a day, so that we can use it for our work. It shouldn't be too invasive. Shouldn't be too heavy. It should provide all the field of view we need, so that we can overlay images in a believable, realistic fashion in our visual field of view. And the resolution should be like 1 arc minute. That is in the ballpark of human visual systems capabilities at the fovea. And it should provide a dynamic range that should work at outdoors and indoors at the same time. This is a very big problem. So I would even say this is a greatest challenge for a wide set of industries. And we can either follow this route, we can either continue pushing this route and try to miniaturize display drivers, batteries, and computers while building a new operating system and finding a new camera and a display and so on. Or we can change our thinking. We can change it in a different way. But how do we change our thinking in this, right? Like, how do we get to a new form of design from here? I asked the same question to myself some time ago, and I looked into augmented reality display devices. I analyzed them and tried to see like what people tried in the past before. People tried near-eye displays, handheld displays, retinal displays. There are even contact lens displays you can find. There are these, projector-based spatial transparent screens, projecting on the walls, and all these kind of displays you can find. To my surprise, there is one thing that people didn't try. That is to project images to a user from a distance without requiring a screen. It can either require an eyepiece, or it can be a direct beaming into the eye. So I will be talking about this idea mainly in this talk, and I'll combine it with computer-generated holography in the coming slides. So let's understand what I'm proposing here. If we take everything off that device, off that near-eye display, I'm talking about computing modules, light modulators, and batteries, all these devices. Let's say we remove all of these devices from these near-eye displays. Instead, we pack it into projectors that you can distribute around, okay? It can be in any form factor. You don't care, because you're not, attaching these projectors to your head anymore. And then we beam optical beams to a user from a distance. Then create this augmentation overlaid on the visual field of view. Of course, in this scenario, a user has to wear some sort of optical component. And at best, these components can be diffractive components that are fairly thin, can be in micrometers thin scale. So basically, you can create a glasses that is, lightweight, and even more lightweight than your prescription glasses, because they're just made out of diffractive components. So this way, I think we can avoid many different problems. Like, we don't have to think about, okay, heat dissipation, or we don't have to think about form factor, because all I'm using is a diffractive component in front of my eye, and the weight is like there's no weight in this. And the power and compute, they can all be on the projector side. If you like, you can add like, I don't know, 2 different computers per projector, as much as you want. So this can help you realize an augmented reality display system that will, be free from multiple different problems that we just discussed. About the heating problem specifically, I want to talk about this a little bit more. If I just take, my mobile phone and just put it here, let's say, and it's in my constant contact, and let's say I'm talking to someone on the phone or something like that. After 10 minutes, it can easily get, to a temperature like, 35 degrees, 40 degrees Celsius. And this is a high temperature. If you look into the medical literature, even this is not healthy. So just think about the requirements of augmented reality glasses. If I place some sort of computer, even if it's a thin client, people like, using this streaming approach and so on. Even if they stream, they would need some sort of, predictive capabilities on those glasses, because, the latency will be an issue. People have to, predict the missing frames on the thin client and so on. I'm not really sure. I'm not really fully buying all these other approaches. I'm not against them. It should be explored. Somebody has to explore it. But all I'm saying is there's an alternative way to fixing these issues. After, designing this thing, we literally go back to the lab and start building stuff. Back in 2021, we built a display for the first demonstrator for this work. And on the left-hand side, you'll see, left-hand side at the top, you'll see this optical breadboard and bunch of different components on this optical breadboard. You see this projector projecting a beam through a bunch of different lenses. And then these lenses are projecting the beam to the steering mirror. And steering mirror helps you shoot the beam in the right direction towards the user. And on the right-hand side, you see this variable, headset, the first version. There's a mirror, diffusive screen, and a beam combiner. You don't necessarily need that mirror on the top, because, if you have your projector at the ceiling, it can project from the top. You don't need that mirror anymore. This is just needed because, the projector at the time was on a table and the person was close to the projector. So something has to bounce the beam into the display in the correct way. That's why we needed that thing at the time. If you make all these things happen with the tracking involved, there's a tracking also involved. This camera is, if you look into the left-hand side again, on this optical breadboard, you will see this camera. It's coaxial, meaning it's aligned with the axis of beam propagation. You can now see wherever you project the beam, right? Then you can speculate if you're hitting the glasses, or if you're hitting a wall, if you're hitting to something else, and so on with your beam. So you can, shine the beam at the right place, find the person, and display the image this way. So if you build all those 2 things, and the result you'll see is shown in the bottom, the image from the perspective of the user. This is we placing a camera at the location of the eye box where the user is placing their eyes. Then you get an image like this one. The image quality-wise, it's almost on par with existing products. It offers 7-8 cycles per degree. So this is a good resolution if you think about current day near-eye displays for virtual reality or augmented reality. However, as I told you in the beginning of my talk, we want 1 arc minute, right? So this is not satisfactory. In terms of resolution, this device has to improve. In terms of the form factor of this eyepiece that I'm showing you on the right-hand side, the headset, it has to be slim, as I promised, right? So these things have to improve. I'd like to take a segue very quick. Please keep this bit in your mind. This is what I just showed you here. I would like to take a quick segue to holography and combine those two things in the next slides. So in the recent years, if you're following SIGGRAPH, Optica, or Nature, Science Advances, all these other places, if you follow these journals quite often, you'll start to see that there's a pattern. People are starting to build holographic displays, and they rely on holographic displays. They build new type of holographic algorithms and so on. And why is that? Like we see some papers that are seminal papers specifically from Andrew Maimoni back in 2017, which was revolutionary at the time because it was offering a slim form factor holographic display in the form of glasses. And for some time we wait until 2020, and then we start to see this happening in SIGGRAPH again, and currently this is an ongoing trend. The reason for we are seeing all these trends taking place at this point is because deep learning came into place, and we can now build much better models with respect to previous cases. We can perfect the imperfections in the hardware using these new algorithmic approaches, new tools, new learning methods. To give you a sense of how dramatic the change is, I found this image from online showing a holographic display from 10 years ago. And this is the visual quality you get from that time with a holographic display. Let's look into today's holographic displays. This is a paper that appeared in Nature 2021. The first author is Liang Xi. It's called Tensor Holography, and the image quality is a captured image from that specific display. There's a dramatic image quality improvement, and we are starting to seeing that holography can be practical for the very first time after so many years. That's why people are getting very excited about holography overall and thinking more about it. So we should ask ourselves how holography could be useful for this new method I'm proposing. If you remember, I was saying that the resolutions of that display wasn't sufficient. Form factor wasn't sufficient. So we should identify new means, to build this display in a holographic way to provide, high resolution images. So of course, in that case, you need to build an holographic projector, and that projector has to project images to a user from a distance. And then we should track the location of that user so that we know where to beam the beams that we are generating, the holographic beams. And we should have an hologram generation pipeline. And then we should have some sort of simulation model that does everything perfectly on hardware. Perhaps in the future, if you want to bring the existing content to holography, we should also start thinking about like how do we do that? What kind of models, what kind of camera models, what kind of representations we need to get these content from existing point clouds, multiplane, or like sign distance function or whatsoever. All these things, how do we get them into the holography? How do we feed these data into holographic displays? A holographic display is like a nerve, basically. It can show you different perspectives in real life. So it's how do we achieve all these qualities of holographic display in such a display? This is an open research question, right? And we took a step further. We built a holographic display. On the left-hand side, you see an eyepiece that is 3.6 millimeter thick, and it's standing 50 centimeters away from that holographic display. And as you can see, I'm just holding my hand and then just measuring it. My hand is like 26, 25 centimeters long, so you can just have the measure like that in that way. So this 3.6 millimeter thickness is all you need in your glasses, plus it's below 20 grams. You don't need batteries. You don't need computational units on this thing. You don't need anything on this thing, to be honest. It's just a passive glasses. And the image quality you will achieve from that 50 centimeters is shown on the right-hand side, as you can see. And We don't have the right eyepiece in place at the moment, but we are slowly getting there. And this can be as thin as 16 micrometers in thickness. Again, the scale is micrometers, whereas the previous stage was millimeters. So the next thing maybe we should talk about, like for the curious people in the talk, they may want to understand a little bit more about how holography works and why they should be caring about holography beyond this research that I'm pitching here. The basic idea of holography is there's a hologram. It can either manipulate amplitude or phase or both. Amplitude is like the amplitude of light, and phase of the light, phase of the electric field. So in a hologram, each point diffracts, and then it arrives at some image plane. As it diffracts and arrives at the image plane, other beams are also, other points on the hologram are also doing the same thing. And sometimes these beams are like coming on top of each other, superimposing on top of each other. They can either cancel each other or they can amplify each other. It can be a constructive or destructive interference. This is the quality that holography offers with respect to, existing displays. And obviously, this display can offer a high resolution image because this interference can give you even, like tiny features on your image if you want your hologram to generate it. Thanks to interference and diffraction, you can do this. And plus, since you can cancel out beams, you can really remove light from the scene. I mean, maybe it's a bold statement, removing light, but removing amplitude, let's say, from the target scene. So you can achieve true dynamic range. That is also another big promise of holography. Also, another promise is you typically use, laser light sources in these displays, and these laser light sources are pure in color. So it can give you if you choose your color primaries in the correct way, can give you a large color gamut, which is not possible with the existing displays. And it is the only technology that I know without any trade-offs. It can display 2D visuals or 3D visuals at the same time on demand. Whenever you like, you can just switch to 2D if you like. Whenever you like, you can get a 3D image out of this thing. And since the final image is shown in this figure, it's a combination of multiple pixels shining on the image plane. Even if one of your pixels is dead, it's not a big problem because the other pixels can compensate for it, and a dead pixel is an ancient relic in this case. And another thing is images that are generated in holography, they are continuous because you're talking about real physical waves approaching to an image plane. There's no pixelation. Pixelation is just your simulation, nothing more. You don't even need the pixels. You don't even need to describe it in the form of pixels if you want. There can be other means to simulate it. So all these promises about holography are not yet fully, let's say, demonstrated. There's really important, advances in this field, but the field has not demonstrated all the promises yet. And we are looking forward to seeing, one single display that has all the qualities we need, right? It will be a realistic visual, perceptual realistic visual. That is an active research problem. That's why, holography is an important venue to look at for graphics folks, optics folks, perception folks, and so on. So, So all these displays they are using, they become, very common nowadays because spatial light modulators are maturing. There are more pixels on the spatial light modulators, so you can even buy a 4K phase-only modulator. It's a highly expensive device. And you have access nowadays a computational resource that is superior with respect to 10 years ago, highly parallelism is in place. You can have like parallel processes running for you, helping you to calculate faster in your hologram generation pipeline. There are even papers, claiming real-time rendering for holography. With all these, holography becomes, again, an important venue and people are looking into it. In the meantime, we derived a library to make our lives easier, and we share it with the public so that other people's lives can be easier if they have a desire to look into holographic displays or holography in general. The idea behind this library is it's compatible with modern machine learning frameworks, specifically PyTorch, and can automatically differentiate given models, right? So it eases the pain of a person, or let's say a graduate student or an expert, when they want to, use machine learning in their approaches, and they want to have a physical, like simulation in place for data generation or for training purposes or for the test time and so on. They can do that with our library. I highly recommend it for people that are interested in this field. And if you want to learn more about it, and if you have some questions, please do not hesitate to ask me offline or at the end of this talk, of course. And to give you some sense, how easy it can be with this model, with this new library. Previously, you were like writing a bunch of different Fourier transforms, multiplications, and then you were taking absolutes and so on, just to propagate beam from one point to another. We simplified it such that you can just call the propagate function, and then it will propagate from point A to point B for you. You don't have to think about, oh, now I need to write this, I need to write that. It's a standard method to solving common tasks at holographic displays or holography in general. So it can ease your pain in development. Then you start to think about, modular things. You don't think about anymore, the nitty-gritty details of each component, but you start to think about, okay, I can put propagation here. This is my image. You can explore so many ideas this way because things are becoming more abstract for you. And we take advantage from our own, medicine, let's say, and we build learned models through this way. And if you look into the classical description of light transport in optics books or computer graphics books and so on, it doesn't account for the imperfections in a display. People try to fix this in the past with using UNet, for example. They take a unit and they say, okay, this unit will be trained such that it will represent all the light transport and it will be effective for our display. Yes, to some extent, this is really, really interesting and a valid argument, especially if you're working on the regimes that generating images really, really close to your spatial light modulator. I believe that because light spreads in a very little amount of space. But if you're propagating your beam for long distances, you need bigger convolutional models. Like, let's say you need more connectivity in between your layers and so on. If you have the right amount of memory and capacity in your network, of course, you can do that, of course. But we ask ourselves, let's take the classical model. Can we improve it such that it accounts for the imperfections? That's what we are doing in this paper. We train a new complex kernel using the data here referring to holograms, and captured images from our holographic display. And we try to see if we can come up with a better light transport kernel, a convolutional kernel that will represent my system in a slightly better form. So far, it shows some promises, and there is room for improving this, of course. And we are looking into it. This is a two-dimensional model, by the way. So for each plane, you have to, train it again and again. There are means to improve this, like 3 dimensions is one thing, of course, but there are other aspects of light that we can account in this model in the future, without thinking of light transport as a black box, but rather thinking of it like in an explainable manner. So the point I want to raise from this slide is computational resources, improvement of computational resources, improved the physics of holography on many different things, of course. So I would like to switch gears to the last part of my talk, and it's mostly about perception. In the last year, we looked into a concept called metamerization, and this is a perceptual concept. Assume you're looking at this red dot shown on this image, and assume this image is wide enough on your display, and you're at the right distance. The things that are painted at your peripheral, at the metamer section, you won't be able to, you won't be able to distinguish if it's the full resolution image or not, because the way the human visual system works in this case, it accounts for statistics rather than accuracy. So if you have the right distribution of pixels at the peripheral, at the right eccentricity, then you can fool the eye looking into a full resolution image. And if you have a lookup table, for example, in a display that has these statistics, instead of transmitting the images all the time in full resolution, maybe you can just say, bring me this statistics, please, and bring me that statistics, please. And then your display will paint it in the way you want it to be painted. That is the concept. So metamers are the visuals, statistically correct visuals, that replaces the images in our peripheral with some other image patches, or like, let's say, with some other image representations and so on. We looked into this and we found a way to simplify this further. And this was a work published at SIGGRAPH 2021. And the idea is to foveate using metamers. Here in this animation, you can see that this little red dot basically is your gaze location, and you're looking into different portion of the, you're looking at the different portion of the scene, and you're following this red dot. And here you can see this, like, how to say this? Maybe it's like a icy glass, right? Like it looks like an icy glass, the peripheral portion. Hopefully you can see this. Hopefully the compression is not ruining the experience for you. So, so the idea is like you won't be perceiving these, weirdness on the peripheral, because this is a gaze contingent in the way described in a way that is statistically correct. So we also add this as a loss function to our library in the recent years, and we build a new computer-generated holography pipeline with it. We ask ourselves, instead of like making 3D display representing all the multiplanes at once, we ask ourselves, can we just look into one plane where the person is looking at, calculate the visuals for that plane in the way it should be looking like, and then rely on, since this is a gaze contingent display, rely on this metamerization process in foveated rendering to represent the images in the correct way that your visual system would accept. We also build a holographic display to test this idea. Excuse me. So we also test this idea with a holographic display that we built in-house. And we generated these visuals with this holographic display, where you can see on the left-hand side, there's a red dot representing the fovea location, the gaze location of a person looking at the first journal on in the front focus. And there's this back focus. There's this blue dot as well. And you can see different portions of the scene appearing differently due to metamerization process. Cool. The next thing is the conclusion slide. And if you're interested in hearing more about our work, if you have any questions, if you want to explore us a little bit more, these are the two websites that you may want to visit. But I can also give you a quick summary of what we have just talked about. I think I argued that displays are essential part of our lives, and it's becoming more and more important, and we have to improve them to improve our lives. And I argued, and many industrial and academic researchers, I think, would agree with that, augmented reality near-eye displays could be the game changer for our next in interfaces, in user interfaces. And I also argued that most of the components that we use in these displays may not be necessary for applications like, automotive, or like, working in front of a table, working in one room, or like sharing one common space, meeting room, and so on. In those kind of applications, you can have this other approach that I pitched in my talk. And I also coupled this with the perceptual aspects, like how you can generate these visuals in a perceptually accurate way. With that, I would like to conclude my talk, and I'm more than happy to answer your questions. Thank you.
Thank you. Thank you for the talk. It was a great talk. So before, while everyone warms up with the questions, maybe I will start. So I was wondering, because I haven't tried an AR device, like state-of-the-art one, for a long time. But one of the things that I thought it was, at least for me, as like experience as a user, one of the things that I felt it was like meh was the thing about the entrance pupil, right? You need to have like traditional AR devices, you need to have like located very precisely relative to your eye, because I mean when you are projecting light to the eye, the moment you project slightly off, you see nothing basically, right? So I was wondering, so for the case you presented for holography and so on, how far are we from like a real scenario, like outside of the bench, like in which you can how accurate does the tracking need to be, so that the projection actually reach the eye and so on? So how far are we from real scenarios?
Short answer is very far. And so the short and honest answer, let's say. I think you bring a really interesting point here, tracking accuracy. Because you're projecting a beam from a distance to a person, even if you make a tiny mistake, it will be amplified on their retina. That's very true. But there must be a ballpark. There must be something that is in the ballpark of acceptable, let's say. And one line of research that could extend this research is in tracking, as you just suggested, like how accurate one can be. What are the perceptual requirements for such a display to be practical? I think these are valid questions and highly important questions.
Mm-hmm. Yeah, and probably perception also plays a role in this kind of questions.
Yep.
Okay, thanks. So we have a question from, let me see the queue, Juan Raúl. Juan Raúl, please go ahead.
Okay. Can you hear me?
Yes, I can.
Okay, so I was wondering when you, you talk about these holograms, no? And basically you say like, okay, we can manipulate the light with these diffractions and so on. But what are the assumptions there, right? Like because I guess like if you have other lasers that is not your projector, I think it will be tough, no?
Sorry, maybe I can take the question one more time because I think I missed some bits. Yeah.
So the point of the holography is like, okay, you have a projector and this projector emit the light, and you don't use a display, so you use this holographic like a figure, no? Mm-hmm. But how this work with I guess that you need to control the lighting condition of the place, no? But what happens when it's like, I don't know, like outdoors, or there is like a other light source in the...
Yeah, so I think this is a valid question. Let me see first if I understand your question. I think you're asking like there is light coming from the projector, and then there is, let's say if you take this to outside, there are some other lights from the outside. Would that cause any trouble? Is that do I capture?
Yes, exactly. My question is if there is other light source in the scene, like artificial or the sun, how this will affect the holographic experience?
Yeah, that's a excellent question. That's an excellent question. So there are these elements called holographic optical elements. These are optical pieces. They come in, transparent films. These are thick diffraction gratings. The way these are being recorded is there's a reference beam and there's this objective beam, and this if you have the objective after recording it, if you have the objective beam, it can replicate the reference beam. If you have the reference beam, it can replicate the object beam. So this is how they play in the real life. And if you have some other beam that isn't objective beam or reference beam, it's not coming from the same direction, doesn't have the same qualities and so on, it will not be modulated by your holographic optical element. Or let's say it will be modulated at a level that will be negligible. So in one case, in one scenario, you can think of an eyepiece that has such elements that accepts, let's think about, for example, prescription glasses. If you have a multifocal prescription glass, you have at one portion, you have a lens just for reading things at really close to you so that you can gaze at it and so on. Let's say we want to replicate such a scenario. So we know where the light is going to come from for that kind of approach. And you can record a hologram instead of having a separate segment on your prescription, a holographic optical element, place it there. As long as the beam is coming from that direction, it will get modulated. Otherwise, it will be like the light that you will be looking at in the natural like case. But does that answer your question, or?
Yes. So okay, basically you can filter the light source kind of.
Yeah,
Like,
I think the best concept. I mean, this little bit more. I think we need to chat a little bit more, of course. But I mean, if you want to do your own research in the meantime, offline or so, I think the right keyword you may want to look into holographic optical element.
thanks.
You're welcome.
Hi, do you hear me clearly?
Yes, I can, Baran.
Okay, thank you for the nice, interesting, and inspiring talk. When I think about displays, I get usually confused. Yes, I agree, displays are how we experience the world behind it. And many things should reflect how we experience the real world, yes. But those are actually controlling how we experience as well, and how our perception is built, also changing. So the new generations are less exposed to HDR content since they are leaving houses less than older people. So how we experience is changing, and the current displays are controlling where we are going. I'm not sure if this evolution would be fast enough, but there might be some effect of those available displays. Do you think it can actually affect the future of displays? And what kind of effect can you think of? And one example I want to say is, again, HDR and LDR thing. We always try to come up with better displays or better tone mapping algorithms, but maybe there is no need because the new generations may not expect. So what are your take on this?
Thank you, Baran, for your nice question. First, I think let's not get so many researchers working on high dynamic range, angry by talking about, high dynamic range not necessary or something like that. But so I think if I understand your question correctly, you're asking, people are evolving with this new setting. The devices are different now, and doesn't have the same characteristics as outdoors or real life. Therefore, we are adapting to it, and we are going to evolve into a new type of let's say human being or something like that. I'm not a biology expert. I cannot tell how the evolution of mankind will be affected from this process, but I believe the evolution process takes a very large time scale. So I would personally expect these things to be negligible given the lifetimes of an average human being. But I may be wrong. Maybe we evolve faster. Maybe someone can tell me, educate me on this front. But I think the current human visual system would like to see high dynamic range. I would say like that, and but not sure if this is a satisfying answer to your question. I think you were looking for something else, maybe.
It kind of answers, but what I mean is, for example, there are not very all the BRDF approximations are not very realistic, for example, and they are not representing the real world as real as possible. And there is some diminished real experience there. And there are many different algorithms that affects the quality of the displayed image. And probably it outputs some image that doesn't match with the real experience. And this is problem for me because when I was kid, I wasn't so much exposed to those displays. But there are many kids that grow up with those displays. So this becomes their reality, kind of. And yeah, I don't know. Maybe there is no huge need to update these displays to match our real experience.
I think you're asking. Do you mind if I modify your question a little bit? So I think you're asking. Physics is like a box, I would say, whereas the computer graphics approach is like more curvy. So you can always, neglect something, avoid something, and things will still look good for an average user. I think that's the question. I think that is the question you're trying to ask, if I understand you correctly. And yeah, you're right. You're right. I mean, there's so many things you can be super, super precise, but is it worth it? Not sure. Like this metamerization approach I showed earlier, like if you don't know that, like you would still be painting images in full resolution in your peripheral, right? Like, and you will be trying to pay attention to the details, and your optimizer will, will do everything it can to paint the pixels in the right way in the peripheral. But do we need to paint the pixels in the right way in the peripheral? Can we relax this optimization constraint a little bit? I think the answer is yes. That's why the perception is a big part of display engineering, I think. Like you need to find new ways or to represent, to have, curvy, corners, let's say. So that I think will always play a key role, and it's important. And yeah, I hope that's an answer to your question.
Yeah. Okay, thank you.
Yeah.
Hi, you can hear me, right?
Yes, I can.
So thank you for the talk. I really enjoyed it. I really like the change of paradigm. And what I wanted to ask is, like, I understand that your approach take inspiration from some of the holographic solutions, but what are the main differences? I mean, what you think is actually easier to improve if like this system with that needs to have a lens or a full holographic system? Because I understand that one of the problems that this system has is to tracking, and also probably the multi-projector problem. And also, I also want to ask, like, if you actually rotate the head, does the thing get worse or no, or it's more or less independent from that? Because like with the holographic thing, you probably don't have these issues. But at the same time, I think there are some hypotheses that you can't make, right?
You're absolutely right. I mean, there are things that needs to be explored. And you're asking, like, what happens if I tilt my head, and how do I keep the image stable in one position? It's a combination of the solution to answer to the question you're highlighting is a combination of how you design the eyepiece, meaning what you place in front of your eye, plus how you generate the hologram. What kind of face pattern did you put on your spatial light modulator? So if you do this in the naive way, naive here referring to I'm just generating an image at some distance away from the projector. If you're doing it in that specific way, then probably the answer would be, like I can rely on classical, image processing tools. Like if the head rotates, okay, I will just tilt the image in the right way, and that will help me to, get aligned with the image as I rotate my head. But you also raised some other questions, like what if there are like multiple projectors? Like, do we need multiple projectors and so on? Yes, you're right. Like if you want to have a 360 coverage, meaning like I turn away from the projector like this, and I still want to see the visuals in front of me, that may require multiple projectors, but it may also not require multiple projectors, because let's think about it like this. If your projector can also be miniaturized, which is an easier task with respect to miniaturizing an near-eye display. There are Pico projectors at the moment that you can buy off the shelf. If you can make something like that, probably you can have it carried around with you. Like many of these displays that we have, like Magic Leap, for example. I will give the name of the company. They have this mini computer attached to their near eye displays, right? So that mini computer maybe in the future is a projector. It's just not a single mini computer, but a projector embedded inside, and you can use that among with your passive glasses that I'm pitching, and that can help you resolve some bits of the problem that you're highlighting here. So one natural thing I like about this beaming display approach with respect to other ones, you can turn it off literally, meaning like you want to see something, you need to bring on this projector with you. If you don't want to see something, your smartphones, all the time. I don't think this is good for people's psychology after a while. So we will probably have some problems in the future. That's I'm guessing. Like if you constantly show people things and so on, it's dangerous. I think, in my opinion. Yeah. Does that answer your question, Dario?
Yeah, pretty much. Thank you.
You're welcome. Sure.
Hi, thank you. Do you hear me?
Yes, I can, Pablo.
Well, thanks for the talk. It was really, really interesting. I have, it's a bit of criticism maybe, because I don't know if you may have look into this concept, but since I was a kid, they always told me don't point with a laser to the eye of the people. As I understood, maybe I'm wrong, but with the projector, you are just projecting the light into the lens, straight to the lens, so it will sort of, with more technology applied on it. For example, if there is more ambient light, for example, I guess this will correct by using more amplitude of the light, so it will get into you'll get the difference to the ambient light, for example. Have you considered these problems that might be caused by projecting right into your eyes? Like, I guess, like the screens, but it's like more straightforward projector. Thank you.
Yeah, thank you, Pablo, for your nice question. I would like to switch back to some other slides that I showed you guys earlier. Just give me a second, please. Okay, this is the slide, I think. Okay, let's look into... so the question you raised is about what if there's more light in the environment and my projector, it might be too dim, right? For, shining the right amount of light into my retina. How do I resolve that problem? So I want to talk to you about one of my previous work from 2017, this one specifically. Hopefully you can see my mouse cursor. And the idea behind that is it contains this holographic optical element that I was pitching earlier. The idea behind holographic optical elements is you need to have a reference beam to generate the image you want. And they are doing this in a highly efficient manner. So meaning these tiny little projectors that are on the side are bright enough to show an image even at outdoors. This we made it work at this very sunny day in California, and it was just showing the visuals under the sun, and you won't be able to I mean, I'm not saying we are beating the sun, but I'm saying that it's applicable to outdoor applications, of course. So the point I want to bring from that project to this specific project is, if you have the right optical element and if it's using the right reference beam, there's a chance that you can do this very effectively, no matter how far you're propagating your beam from. Like, even if you propagate it from a meter away, that's okay, because this holographic optical element is designed to do this in the effective way. That is a short answer to the brightness question, but I'm not sure if this satisfies. But yeah.
Well, it was just a concern, like, what will happen if there is too much light into the environment?
Yeah.
And if that will hurt somehow your eyes or your retina or whatever.
Yeah. I mean, the projector will always be bright enough if you use the holographic optical element approach that I'm pitching here. Mm-hmm. So you can easily meet 500 candelas per meter square, for example, in terms of brightness, which is a brightness of a mobile phone. and we can operate our mobile phones at outdoors without any problems so far, let's say. I think that same condition can be satisfied by using this optical element that I'm pitching. And yeah, hopefully that's an answer to your question. But
yeah, it does. Thank you.
Yeah, you're welcome. Yeah. Thank you, Anna, for having me here today. And I really enjoyed the conversation and also the questions. In case you guys want to reach out to me, please do not hesitate to do so. You can visit these websites and find my email. My doors are open to any questions. Okay. Thank you, guys. See you guys. Bye.